We will delay everything half an hour. So now we will start with Professor Laura Lotero from the National University of Colombia in Medellin. And let me introduce the chairperson of today afternoon, Professor Fernando Naranjo. So please remember, it's 15 minutes for each presentation and maximal 5 minutes of questions, no? So maximal 20 minutes in total. So thank you very much and enjoy.
Good afternoon. Then the next talk is by Laura Lotero. She's coming from the Universidad Nacional de Colombia in Medellin. And, um, and this talk is about, sorry, Laura, how we move in the city, some results of the analysis of complete mobility networks. Then you may begin, Laura.
Thank you, Fernando. Thank you, Jose Daniel and Gabriel, for your invitation. I hope you are hearing me well. It's a pity not being there in Bogota with you this afternoon. So, in order to keep track of the schedule, we're going to talk about mobility networks. And this is the main motivation is that understanding and modeling urban mobility is crucial for many things, from urban planning, decision making, transportation science, public health, etc. And urban mobility is the result of multiple connected elements uh, that, due to their interconnectedness, produce and exhibit nonlinear emergent behavior. Therefore, it is a complex system, and that is why it's very interesting to analyze. So, in order to understand this talk in terms of this workshop, we were wondering what interesting patterns can we find by representing the movement of people within the city through networks. And through networks, we are using concepts and tools derived from statistical physics. So, let me introduce you a bit of human mobility. We can study human mobility according to the scale, for example, global, continental, national, intermunicipal, or urban. This is the human mobility that I am interested in and that I have been researching. What for? You can study human mobility for urban planning, transportation, planning, public health, marketing, a lot of things. And you can study human mobility according to different data sources. For example, surveys, origin destination surveys, taxi GPS, or this in-driver or Uber GPS, and on all these intelligent systems, from metro and subway cards, from banknotes, money, card transactions, credit card transaction, from social media, from mobile calls. Every time you are using your phone, there's a signal sent to one tower, and you then they can have some information about where are you in parts of the day or in parts of the city, and also from historiography, from diaries and autobiographies. But this study is more from the historians. So my first attempts in understanding and analyzing urban mobility networks in Colombia was when I was doing my PhD. I studied 3 cities in Colombia: Bogotá, Medellin, and Manizales. These 3 cities are very different in the size, in the population, in the area, but we had the origin destination service for these cities in 2005, 2012, and we constructed networks. So we analyze all these things that are very interesting in networks. For example, the degree distributions, the strength distributions, everything. We started to understand, to see what excuse me, many properties of the network. So you can see, for example, in these three cities that there are, for example, you can um, identify like a exponential distribution for the strength of the nodes. So we see that it was interesting, but beyond the common laws for saying that we found in these different cities, we were asking ourselves, is urban mobility the same for all? And the first approach that we took was to analyze transportation modes and socioeconomic strata. And we see in this graphic, in this plot, that using this origin destination service, you can see, and you can see it in the streets, that people from the lowest income, in both in Bogota and Medellin, use, for example, walking or transportation system, public transportation system, more than, for example, the wealthiest that use their private cars. We also started to analyze the differences in how people move according to their strata, and we saw that different socioeconomic classes started to move very different in times. For example, or for instance, stratum 1, the lowest income householders, started to make their travels earlier, much earlier than extratum 6, which is the wealthiest. So there is a organization, let's say, ordering of the mobility according to socioeconomic classes. We started to see what kind of spatial differences or spatial patterns can we found in urban mobility, and we found that, for instance, the extreme strata, status 1 and status 6, this is Bogota in 2012, in 2012. The extremes are very located and move very specifically in some specific zones. But mid socioeconomic stratum move throughout the city. Then we were wondering, what about gender? So we started to analyze gender patterns in human mobility in Colombia. We use both Medellin and Bogota data sets, but here is Medellin, one origin destination survey in 2005 and the other in 2017. The good thing about these huge and large surveys is that they have to be updated according to law. So in this graph, we see that women tend to make shorter travels than men, and they avoid to travel to certain destinations during late hours. So there are differences throughout the day for gender. And we proposed, or we use a modified version of the mobility diversity proposed in 2015 by Papalardo and others. This is the mobility diversity, and we wanted to see how different or how diverse are the mobility by gender. So if you, knowing that this is a workshop on statistical physics, I guess you might recognize this kind of formula. It regards to Shannon entropy, and it's 0 when all people move to the same location, and it's 1 when it is equally distributed through all the population zones, through all the neighborhoods, let's say. So we compare the mobility diversity by men and by women, and we see that For example, we used this mobility diversity for Medellin, for Bogota, and also for Sao Paulo in different years. And we see that men have more diversity in their travels than women. And it happens both in Medellin in every year that we took this survey, for Bogota and for Sao Paulo, except Sao Paulo in 2007. That is out of the, it's the strange one. But the rest of the years and the cities, it remains this phenomenon. And you see that also gender differences in this diversity get smaller over time. Um, so this is an interesting pattern that we found. Also, analyzing gender, but in other case, not using origin destination surveys for the whole city, but analyzing the origin destination for bicycle share system that is called Encicla in Medellin. We used the 2019 data. That was, they gave us the origin destination of a typical day. This is the system. I'm going to rotate it so that you can see the map. And there are differences by gender, starting that by, because men use much more this transportation system than women. Uh, Almost or near the 80% of travelers or users of this system are men, while only 20% are women. And you can see here in the left side the mobility network using this uh, bicycle share system of men and of women. So there's besides the sharing or the percentage of use, there are different zones according to gender. Also, we studied spreading processes and human mobility, and this was before the pandemic. So, given that there was a high impact research and diseases spreading due to human mobility even before the pandemic, and our results on urban mobility and socioeconomic segregation, that we have seen that different socioeconomic groups move different in the city, we proposed a multiplex network, being the nodes geographical areas and being the layers, these different mobility patterns of the different classes. Let's say, for example, or for instance, socioeconomic strata. So we can include this heterogeneity of metapopulation. So we can see these different ways of moving of these different classes of these different ages, and we see that the social mixing between classes and mobility, the mobility is very important for this. Uh, Human mobility during the pandemic. So it was before the pandemic, and we saw and we suffered that during the pandemic, human mobility was very restricted. So there was a significant decrease in the use of transportation systems. So we analyzed the case of Transmilenio in Bogota, because there was a risk of disease spreading in one hand, and in the other hand, there was a financial and economic sustainability risk of the system. So we used the car tabs from February to December in 2020, and we constructed one network, assuming that the last tapping point in the day, so if I move from place A to B in the morning, and from let's say B in the afternoon, the B tapping in the afternoon was the destination, or was the destination node of this mobility network. So we had almost 330 networks, and we wanted to compare these different networks. So we clustered according to their centrality. We use the page rank centrality of each node, that each node is a transmillennial station. You can see here the yellow points are the nodes, the stage, the validations or the use of Transmillennium before the pandemic, and then you see the lockdowns and late recovery, early recovery when the system was open to recover the economy in the city. So we analyzed also the changes in these mobility networks, and we see that the changes during the baseline and the lockdown during COVID respond to spatial and socioeconomic patterns. I have not much time to explain this, but this is the reference to see this uh, very interesting analysis. And some final comments says that using networks allow us to represent mobility data in a compact and efficient way for finding interesting patterns. For example, there are common mobility patterns regardless of the city of or the year of the data. However, if we look closer, urban mobility displays different patterns according to some attributes of the traveler or the trip. Transportation modes, as we might imagine, spatial segregation patterns according to socioeconomic strata. This explains how and where we move, if we are rich or poorer. Uh, and we saw also that men and women move different. They have different diversity, how many places they visit, the travel times when they travel, and travel duration for how long. Being women, the shorter trip makers. And finally, mobility patterns are important for the spread of disease modeling, and changes in mobility patterns also respond to other urban and demographic characteristics, even when extreme events such lockdowns occur. So there is a two-way, very interesting relationship between mobility and the city form. And that's all. I hope I could meet the time of the schedule.
Okay, thank you. Thank you, Laura.
Thank you.
Questions? Okay.
Thank you, Laura, for the talk.
Thank you.
So, how universal are your results? I mean, these are taken in Colombian cities. How do they compare to cities all over the world?
Okay. This is a very interesting question. I have only had in my hands the data from Colombian cities, and also with some collaborators from Brazil, the Sao Paulo datasets. But if you read the literature about human mobility, you can find that there are um, common results, let's say. And as they are very common, they are also trying to propose a universal law of mobility, human mobility, let's say. But we are not yet in that point. But there are a few attempts to getting this universal law for human mobility.
Okay, other question?
Thank you for the talk. I'd like to know. It wasn't that clear for me. What was the usage you did for the Papalardo's formula that you mentioned? I mean,
Yes.
you showed us a lot of graphs theory, but I wasn't that sure. What was
Okay.
the
Yeah, it's because it is very short time. It's just a glimpse of works regarding mobility, but the Papalardo mobility diversity we used in this sense. There's this diversity index that it's according to X, the class of the traveler, and we use, for example, men and women, and with a specific purpose. So we compare all travels, work travels, because we were interested in seeing the gender differences, and if they might gender differences in mobility, and if they can influence the possibilities or opportunities, economic opportunities for women regarding work opportunities. So that's why we adopted and used this diversity, because if women or men or different classes can explore the city, the landscape of the city, like visiting different um, places or zones or neighborhoods, they might be exposed to different things. And if we analyze, for example, work travels, we assume that these groups or these classes might be exposed to different alternatives or opportunities. Uh, I'm not sure if I answer your question or if I need to explain further. I don't know if it meets your.
But for example, with this diversity you mentioned, is that the
Mhm.
same as the variance or something like that used in this distribution that you have there in the figures that you're showing? For example, what's the difference with
Okay,
another
that's
analysis, another kind of analysis that you can perform in this
okay.
kind of
Yeah,
distribution?
we yeah I yeah I also didn't mention that we use bootstrapping because we had only surveys. So surveys are supposed to be only a sample of the whole um, population. So in order to try to expand this sample to some kind of a population measure, we use bootstrapping, like we randomly selected parts of these surveys, and we computed randomly this uh, mobility diversity. And that's why we have these distributions, these probability distributions the of this index, of this diversity index.
Thank you very much.
Okay, thank you.
Okay, thank you, Laura, again. Uh, Please.
Thank you.
Okay, the next talk is by, sorry, Luis Eduardo Olmos. It's virtual? Oh, sorry.
Yes, I'm here.
Okay. And this talk is about the urban traffic dynamics through the lens of percolation theory. Okay. And then you may begin, Eduardo.
Okay, so do you see the presentation? Okay.
Sí.
Okay, and you see the pointer, right?
Yeah.
Okay. So thank you all for being there. Thank you, Daniel, for the invitation. And today I want to talk about how percolation theory can be useful to understand some of the urban mobility problems. So I will introduce the ideas using three short stories in which the concept of percolation is the main actor. Uh, okay, so no surprises. This is the structure of the talk. It's basically the three stories. And let me start with the first one. Some years ago, the World Bank proposed to us to research on two crucial questions in the field of sustainable mobility, and they were interested in promoting the use of bicycles as a transportation method. So they also wanted to use Bogota as a case study, and you know, Bogota is one of the cities with the highest rates of bike trips in the world. So the two questions they asked us were the first question was how to estimate the potential demand for the bicycle trips, and the second question was how to plan the bicycle network, you know, the bike path network, what we call in Colombia bici rutas. So to address these questions, we had access to the records of an app, Baico. This app basically uh, this app, I mean, this data set is the records of the GPS traces of many bike trips in the city, and then with this data we could extract the patterns of those trips. So the second data set was the origin destination matrices for Bogota. Uh, that was extracted from the CDRs, I mean, for the cell phones in both. So in order to answer the first unknown, we combined these two data sets and we applied a rejection sampling algorithm to the origin destination matrices. And then we sampled the trips that had a distance distribution similar to that of Baico. So here you have the travel distance of the bike trips in the app. And then here in red, you have the distance, the travel distance from the CDR's origin destination matrices. And then we apply this algorithm in order to sample these trips, the total trips in Bogota, and extract some trips that had the same distance distribution. So we interpret this potential demand as all possible trips that could be made by bicycle, and then with that potential demand, we use the OpenStreetMap routing machine for routing that demand. And the output is this network that you see here. And this is a network of flows in which each street has the number of trips that pass through it during the day. And you can see the width of each street represents that volume of trips in the world. But if we have this, how to determine on which of these links we need or we propose to construct or to build the bike path. So that's the second question. And the premise in this time in this world was to design a bike path network that better serve our potential demand, as we defined it in the last slide. And but we also demand that we demand the global network connectivity of the proposed network. So in order to propose the network, we define a threshold queue in a way that a link with a flow uh, which is higher than the queue, then that link becomes susceptible to intervene, right? So for high queues, then what we see in the network is that the network is fragmented in a small cluster, as you see in this group. And in the opposite case, if you define a queue very low, then almost every street or every link in the network is susceptible to intervene. So what you see here is the process of the cluster aggregation in this method. So we start with a very high queue and then decrease the value of this queue and see what happened with the cluster that is formed in the network. So in this plot in the middle, you see the size of the two largest clusters in the network. In magenta, you see the largest, the first largest cluster in the network, and in green, you see the second largest cluster. So what you see here, almost in 2,000 trips per day, what you see this big jump. What is happening here is that the second largest cluster merged with the first largest cluster. So you see this aggregation process in this plot, and we determine that for a queue almost 500 trips per day, is the optimal field at which the proposed network span across all the city. So in that work, we then show that this proposed network uh, had benefits in terms of service for the community in Bogota. So in the second story related with the collapse of the urban traffic. So in that time, we were interested in the propagation of traffic jams in cities, and we focus on a specific target group of vehicles that start the trips within the peak hour. Uh, the peak hour, let's say 7 to 8 a.m. So what we see, and which was remarkable, is that after a loading period, after a loading period of these vehicles entering in the road network of the city, then the number of those vehicles, the number of the target group vehicles still in the road follows an exponential decay, as you see here. So we validate that discovery with data from surveys and also with a very realistic micro simulation of Melbourne in Australia. So what you see here is the result of our own simulations, and we propose a very simplistic cellular automata model for 5 cities, and we use, in order to simulate the traffic dynamics in those cities, we use the actual demand for those cities. And we have this exponential decay. So we can interpret this relaxation time like a metric for traffic congestion. So for instance, here we have Boston and Porto. These two cities are the cities with very low traffic congestion, and Rio de Janeiro and San Francisco are the cities with the higher problems in congestion, in traffic. But that is one part of the work of that work. But what we interested, we decided to study the collapse of the network, not the specific traffic jams in those cities. So we ask what happens if we increase the demand while maintaining the spatial distribution of the demand. So what we see here is this plot is the same plot, is this same plot, but this is a log scale, and then we increase the demand and see what happened with that exponential recovery, right? So what we observe is that when we increase the demand, then that exponential recovery transform into a power law recovery, and then that power law is characterized by the critical exponent alpha, and then beyond this value, beyond the value of this critical demand, the decay, the decay of the number of vehicles in the city becomes extremely slow, and the network collapse. So this is a phase transition, and what we see in the network is that there are very large jams that take too many time to dissolve. But this behavior, the behavior that in which the exponential decay becomes in a power law decay, it's a typical characteristic of the directed percolation systems. So we use the framework of the directed percolation to study this kind of transition. And what you see here is, again, the number of vehicles still in the network, but for very long time. And this is the relationship between, the ratio between the demand over the critical demand, and you see the typical curve of phase transitions. So if we study the criticality at the vicinity of this RC, then we can extract the critical exponent beta. So we can characterize that phase transition with these two exponents, beta and alpha. And here we have the plot that we obtain for every city. And what we see is that, for instance, that Boston, which is the city with a very low traffic congestion, it also has a high value of beta. The line here corresponds to the beta reported for two-dimensional systems. So Boston, in a sense, behaves like a two-dimensional system. And in the case for Porto, for instance, here, it behaves like a one-dimensional system. But uh, in general, what we discovered that is that there is a phase transition. There are three phases. There are three phases of traffic, and we call the free flow, the traffic jams phase, which most of the cities in the world are here. But we characterize the transition between these traffic jams and the network collapse. Yeah. But what happened in the realistic scenario for the cities? And that is what the third story is about. And the third story is related with the traffic percolation. So I have to say that I was not a member of the team of this work, but I am involved right now in a project related with this topic. So in a seminal work from 2015, this paper studied the urban traffic of a part of Beijing. So they had the speed of every link for each minute during the day, and they define a ratio between its current, between its current velocity and the maximal velocity measured on that day, right? So in the graph, what you see is that links, red links are links with very low speed, and green links represent good speed, right? So what it is interesting is that they invented a threshold. Again, this threshold is very similar to the threshold that I showed you in the first story. Actually, we were inspired by this work. So if the ratio is lower than that threshold Q, then you turn off the links. Otherwise, the links remain active, as you see here. So if you don't care about the threshold, for instance, if you have a threshold very low, uh, then you all the clusters are connected, right? So in other words, if this Q is very low, you can go everywhere in the city. But if you increase a little this Q, for instance, in here in B, then you cannot go everywhere. If you are in a green cluster, for instance, in this green cluster, if you want to go to the blue cluster, then you can do it, but you will suffer congestion in traffic. So what you see is a very similar, this is the percolation process. This is typical for percolation process. And what we see here, this is the specific, practically, this is the same figure that I show you in the first slide. So you see a big jump in the second largest cluster, and you see that the reduction or the increasing, depending on the way that you see here, when the the largest cluster in the network becomes very low, very small. So this point, this jump represents the critical value of Q. And what is very interesting is that Q obviously varies during the day. So here in this plot, you see in orange, you see that the values of Q during the day varies during the day, of course,
Sorry,
but
Luis Eduardo, you have 1 minute.
okay. So you see that the lowest values of Q correspond to the peak hours in the city. But what is interesting is that they also found that the bottlenecks that breaks down the system into several clusters are almost the same for each period of time. So for instance, in the morning, these arrows, red arrows, are the bottlenecks that break down the traffic dynamics, the traffic inside the city in the morning. But there are others bottlenecks in the noon. So we can use that information to improve the traffic flow because you can see when the traffic percolation appears. So this is the last slide, and maybe this is the inspiration of this talk is because this topic is very hot right now. I mean, there are many groups around the world and trying to to study this kind of transition. But what is very, very important is to try to connect these two schools. I mean, we have now a school from physics, for physicists that understand the traffic as a percolation process. But if you see the old school, I mean, the school from the engineering, then they had their own approach called macroscopic fundamental diagram. So okay, I don't have time to explain this, but basically, if you understand or you prove that there is a connection between these two approaches, then you are contributing very much in this topic. So the conclusion is basically is that we are in a world that almost every system can be translated into networks, into complex networks, and then in that complex networks, the percolation theory is a very useful tool to study and to understand the processes in those networks. So thank you.
Thank you, Luis Eduardo. We have time for one question. José Daniel.
Thank you, Luis Eduardo, for the presentation. I would like I was wondering if this intermediate phase, yeah, for the traffic congestion is similar to the one you found in the BTW model.
BT Doluman,
In the Birham, sorry, in the Birham model.
okay, yeah, that is a very, very long time. Yes, it is related. I mean, in traffic, it is very interesting field for physicists because they have a lot of critical phenomena inside. So what we have is an intermediate. The congestion is not a very delimited phase. So you have unstable phases inside the congestion. So yes, the BTW model is very simple, but that intermediate phase is related with this phase transition.
Thanks again, Luis Eduardo.
Yeah.
Okay. The next talk is by Alejandro Pérez Riascos from the Universidad Nacional de Colombia. It's about discrete time random walls with the stochastic restart on network with resetting. Sorry. Okay.
Good afternoon. Thank you very much for the invitation. I'm glad to participate in this workshop. I'm going to talk about discrete time random walls with the stochastic restart on networks. I'm Alejandro Pérez Riascos. I'm professor here at the Department of Physics. And the main motivation for this research is the understanding of dynamical process with the stochastic resetting. In the first part, I'm going to define what is a random walk on a network. Then I'm going to introduce the concept of stochastic resetting, and then I'm going to present some conditions necessary for optimal restart. Here we have some examples of networks. Networks are very important in the study of complex systems, and networks formed by a set of nodes, here represented by different points, and links connecting pairs of nodes. As you can see, with this definition, we have different structures, and we want to explore a random walker on networks. To this end, we need to define a matrix. This is the adjacency matrix of a network. Here, This is an example for a network with 5 nodes. And all the connectivity of this structure is represented by this matrix. Here we have ones representing the edges in the network. For example, here we have this one due to this link between 1 and 2. And with this information, we can define transition probabilities between nodes, something like the Brownian motion, but now in a network and in some of these structures. And the main definition here is the transition probability to pass from node I to node G. This quantity is proportional to the respective element of the transition matrix, like this. And here we have the degree of a node that gives us the number of neighbors of the node I here. For example, here we have only one neighbor, the degree is 1. Here we have 2 neighbors, the degree is 2. And with this information, we can define the random walker. Here's the Monte Carlo simulation of a random walker on a Cayley tree. This is the typical example of a random walker. And you can see here in blue is presented the position of the random walker, and in yellow is presented the visited nodes. And you can see that this random walker is trapped in this branch of the Cayley tree and requires a lot of time to reach this point and visit other branches of the tree. And there are different quantities of interest in the study of random walkers. We have the stationary distribution. This gives us the probability to reach a particular node of a large times. We have the mean first passage time, the cover time. This is the time necessary to reach all the nodes of the network. And the concept of random walk on networks has different applications, for example, in different algorithms in data science. For example, in the ranking of nodes in Google, to describe chemical reactions, in the understanding of human mobility, for example, in bike-sharing systems, in the mobility of taxis, and there are a lot of examples. But the important here, this is the my main goal to understand this new random walker. Here we have random walks with reset or restart. We amplify these new dynamics with a tourist visiting different sites of a city, following the random walk strategy. But with probability gamma returns to a specific node, here is the hotel, returns with this probability to this hotel and continues with probability 1 minus gamma, continues with the random walk strategy, with the usual random walk strategy. The important part here is that this new process is defined also by a transition matrix here. This is a combination of this transition matrix that describes the random walker without reset. And here we have a new matrix that includes the reset to the node R. And here with gamma, we have the probability of restart. And I'm going to present another Monte Carlo simulation of this process. Here we have the random walker at this initial condition. This is the node where the reset is going. Here is the reset node. And this is the Monte Carlo simulation. Here we have a probability of reset gamma equal to 0.05. And you can see that now the random walker is not trapped in one of the branches. Now with the reset to this node, the random walker is capable to visit all the branches of this Cayley tree. So the main result in our research is that in some cases, the reset improves the capacity of the random walker to reach a defined target. And we want to study this analytically. To this end, we study the mean first passage time. This is the mean first passage time, the time that gives us the average time to start at node I and reach for the first time the target at node G. This is the analytical expression. All these are information of the right eigenvectors, left eigenvectors, and eigenvalues of the transition matrix that describes the dynamics without reset. So with that information, we can calculate analytically analytically this mean first passage time. And with the introduction of stochastic reset, we can see here that this quantity is the same, but now we have here the probability of reset. This quantity also changes. Now we have an additional term that is proportional to gamma here, and also includes the information of the restart or reset node. And once we have the analytical expressions for the mean first passage time, we can plot this value as a function of gamma. Here, the initial node is the center of the Cayley tree. And at different distances, we have the target node codified with these colors, and we have different curves. You can see that in all the cases, there is some gamma that optimize the process, having a minimum, for example, here or here we have a minimum. And always, in this case, the reset always improve the dynamics in comparison with the result with gamma equals 0. But we can study this analytically. We have the analytical expressions for this. So we want to answer this question: under what conditions does reset reduce the mean first passage time? Since we have this expression and we can calculate this derivative, we have an analytical expression for the optimal reset, now represented as this, and the optimal reset fulfills this equation. We exemplify the solution of this numerically. For a ring, we have a ring here, and the distance between the initial node where the reset is produced and the target is codified here with different colors, and we have different curves for the mean first passage time as a function of gamma. Here, the solution of this is represented by these points here that, as you can see, are the minimum of the mean first passage time. So we have an expression, but we can use this expression, this analytical expression, and analytically we can show that this new quantity that includes the information of the mean first passage time here, here, and a new quantity, this value. With this information, the necessary condition for optimal reset is this. Here, there is an important quantity. This is the average of the square of first passage times. This is a new quantity in the literature of random walks on networks, but it is possible to obtain this value analytically. So with that information, we can calculate the different quantities involved in this equation. And we have, for example, here the left side of the equation. In black, we have this, and in green, we have the right side of the equation. We have this, and at the intersection, we know that the condition for optimal reset is fulfilled. Here we are studying the dynamics on a Cayley tree. This is the initial node, and this is the target. And we check that in this case, our analytical approach that produced this optimal reset is this point that in fact is the minimum of the mean first passage time. Also, we have a condition that doesn't require the evaluation of these quantities for different gamma. Now we have an inequality that includes only information of the process without reset. In this case, this inequality is fulfilled because this part now in blue is higher than this part in red. So we know for this condition, we know that the reset in this case reduces the mean first passage time. This is a different case where when the resetting increases the mean first passage time, now we have the initial node here, and this is the target. And in this case, these two curves in black and in green never intercept, at least now for gamma lower than 1. And also we can see that now this part in blue is lower than this part in red. So in this case, it's not fulfilled this condition. And when we see the mean first passage time, we have this result that in this case, the reset does not improve the capacity to reach a particular target. So as final comments, we have a formalism to study random walls with reset, and all the results can be explored analytically using eigenvectors and eigenvalues of the transition matrix. We have a condition satisfied when the dynamics with restart optimize the mean first passage time. This is the condition, and this condition requires the evaluation of a new quantity in the literature, but we have an analytical expression for this, and you can see all the details in this paper published last year. And finally, if you want to discuss this, you can contact me. This is my email. Also, all the papers I mentioned here are available in ResearchGate. And thank you very much for your attention.
Thank you, Alejandro. Questions? Okay.
I would like to know if there is a way to know if the resetting is going to improve, or like you say that there are, like depending on the node that the reset node, it could improve or like worsen the outcome. Is there a way of knowing that this prior to doing the resets?
This is the condition. If this condition is fulfilled for the dynamics without reset, you know that in this case, with this initial condition and this target, the reset is going to improve the dynamics. Yeah.
I have a question. You use this mechanism for other networks, for example, escape free and other factors?
Yeah, this is only for due to the time, the limited time. I present only the results for rings and K trees, but we have the results for Weierstrass networks, for Barabasi-Albert networks, and also we have analytical results for different structures. Yeah, so yeah, the results are general, and we have a lot of networks explored.
One more question.
Hi. Sorry, if you put it on a just sort of regular lattice in 1D or 2D, do you recover the results for like diffusion and resetting?
This is a particular case. This is a ring. This is the one dimension with periodic boundary conditions. But the formalism can be extended to a torus. For those regular lattices, we have the eigenvalues on eigenvectors, and we can apply this approach to obtain analytically the optimal reset.
With the like the continuous case where you have just diffusion.
My main goal is to understand networks, but different researchers are interested in the continuous limit. So,
okay, hello. Thank you again. Okay, the program changed because this morning one person don't stay here. Where are? Okay. Then the next talk is by Felipe Segundo Abril. From by the Universidad Nacional, and the talk is about generalized fractional Feynman cut formula.
Hello, everybody. It is an honor to stay here. My name is Felipe Abril. This work is carried out with the collaboration of Professor Carlos Quimbay, and the name of the talk is Generalized Fractional Feynman-Cat Formula. Okay. The main objective of the main purpose of the work, uh, sorry. The main purpose of the work is to generalize a famous equation that is Feynman-Cat formula that corresponds to um, dictionary or a correspondence between partial differential equations and Ito diffusion processes. For this objective, we are going to use the fractional stable processes, that is a type of stochastic processes, and the path integral formalism developed with the stochastic approach. Here we can see the Feynman-Cat formula in the first line, in the solution. um, we have the solution of a partial differential equation expressed as an expectation value of Ito processes that is in the equation below. In the other graph, we have another um, features of the anomalous diffusion that is in the down the fractional Brownian motion, the realization of different fractional Brownian motion, and in the top is the Levy flight distribution that has the property that have fat tails and long correlations. Um, Also, another property that is important is that in many of the works developed in diffusion processes is that the Kramer's module expansion is truncated to the two first orders, but here we are going to show that this expansion is carried out with all derivatives that is in the expansion in the equation. Um, if you consider in some cases the fractional derivatives. Um, so for this purpose or for this objective, we are going to use the Parisi-Sourlas method, that is a representation of a bigger theory that is the stochastic different supersymmetry of supersymmetry theory of stochastic dynamics. And the idea is that we can construct a path integral approach using the expectation value over the noise eta and the evolution of equation that is a Langevin stochastic differential equation. Here, if we can see, we have a Jacobian that we are going to calculate in the next step, and also we have the Langevin stochastic differential equation where the noise is an additive in the I mean, is the coupling in a deterministic part F, and the noise it. The noise is in principle arbitrary. Um, Okay, for this purpose and an interpretation of the stochastic path integral, we are going to use another statistical function that is the cumulant generating function. For this, it is important to know that the Fourier transformation of a probability density function is the characteristic function of the distribution, and the cumulant generating function is the logarithm of this characteristic function. Also, with this characteristic function or the cumulant generating function, we can record the moments of the distribution through the derivatives of the characteristic function. Another aspect is that for Levy flags, we don't have probability density function in terms of usual functions, but it has an analytic characteristic function. So for calculating this path integral here, also we know about the regularity condition, that is the name that we give it to this condition, that is represented as the existence of the solution of the Langevin stochastic differential equation when don't have a deterministic source. That is, sorry, that is when the f is equal to 0. So with this condition, we can parameterize the solution of the path integral independent of the stochastic calculus approach, that is Ito calculus or Stratonovich calculus. When we have with a parameter gamma equals 0, we record the Ito calculus, and when we have the gamma equal 0.5 or 1/2, we have the Stratonovich calculus. The important point is that the Jacobian in this approach is proportional to a derivative of the function f. After these two steps, we can construct the transition probability of the system, and we have the expression. But in the simple case, when f is equal to 0, we record another result that is in the Kleiner result. Kleiner is a physics, German physics, that works in path integral. And with this approach, we have a simple integral where we can calculate the evolution of the probability density function. Here we have a figure when we have Levy flags, and we can see after the times evolves, the peak of the distribution is small. What is the interpretation of the stochastic path integral? If you see here in this equation, the path integral is proportional to the cumulant generating function, denote BH, and in this order, we can assume, or we can show that the stochastic path integral have the same meaning as usual Feynman propagator. That is, the contribution of path integral is a sum of all paths that have fixed endpoints, but the difference is that here the phase have another phase that is proportional to the cumulant generating function. Another important aspect is that in the case of a Gaussian distribution, we have the cumulant generating function is proportional to p squared. So we can say that this a general interpretation of the stochastic path integral independent of the noise of the system. So the idea is how we can generalize the Feynman-Kac formula for have also long correlations. The long correlation for the increments of the process, because in many of the process of the physics and in the complex systems, we have that the increments are independent, but this is not the reality for many systems in the nature. So here we have the Feynman-Kac formula, as we say above. This is a correspondence between partial differential equations and Ito processes through an expectation value that is represented with a terminal condition, and also through the diffusion processes that have a deterministic part with f and a stochastic part with the function sigma. After all of this, we can construct the fair approximation, the Fokker-Planck for a stochastic path integral. And with this approach, we can record some results that is have in another works. Here is a work in a statistical journal where the Fokker-Planck equation is constructed through the Levy distribution. But the important point is that the form of these works or other um, sources of noise is that the term comes with the cumulant generating function. So, as I say, when I have a fractional derivative, we can construct a process that has long correlations. For this, we are going to talk about the Horst exponent and fractional Brownian motion. A fractional Brownian motion is a type of stochastic processes where appears a measure of long memory of the process that is called a Horst exponent. The Horst exponent is zero point 0.5 for Brownian motion and have another values that is between 0 and 1 when have another type of processes. When Horst is lower than zero point 0.5, we have anti-persistence in the time series, so the series in the future tends to reverse the trend at the present. And in the other case, when Horst is higher than zero point 0.5, the value of the series in the future tends to reinforce the trend at the present. Here is a definition of the Brownian motion using fractional calculus. We have an fractional derivative that is a Riemann-Liouville um, fractional derivative, where the function gamma is the generalization of the usual derivatives, and the measure of the integral is over a binary noise. Also, we have in the figure the fractional Brownian motion realization for different Horst exponents, where we can see when the Horst is near to 1, the peaks or the jumps in the time series are more abrupt. So this approach we can generalize through this type of stochastic processes, fractional stable processes, where the fractional derivative or integral, fractional integral um, is made through an alpha stable processes. Here we can see the same cumulant generating function of alpha Levy distribution, but the difference is that we can have another parameters that is the skewness beta, the scale parameter sigma, and the stability parameter alpha. When we have different values of alpha, this is a mistake in the first figure. Notice lambda is alpha. We have that alpha, the stability parameters, control the peak of the distribution and the fat tails. And also we have the skewness, control the asymmetry of the distribution, and sigma control the scale of the distribution. Also, it is important that in this definition, we have long correlation through the order of the integral of the fractional integral. Uh, for we record the um, usual processes, we have that the Horst equal 1 over alpha. We don't have uncorrelated processes. And finally, when we make the generalization through the stochastic path integral, the regularity condition change with fractional derivative, the Jacobian change through fractional integral, and finally the Langevin stochastic differential equation changes through a fractional integral. And this is the result for the generalized Feynman-Cach formula for a fractional derivative, where we can see the usual form, that is in terms of the cumulative function, but the difference is in the temporal derivative, where we have a local fractional derivative that has the properties that we can calculate through this limit, and the Langevin fractional equation is the established here. So this is the result of the talk, and thank you for your attention. Thank you.
Thank you, Felipe. Questions? Questions? Thank you, Felipe, again. Okay. The next talk is with Rafael Hurtado by from the Universidad Nacional of Colombia, and is related to emergent properties of chess openings. Then Rafael.
Okay, good afternoon to everybody. Okay, we are going to talk about chess. I worked with Gustavo Munoz. He's a former student of our master degree in physics. Uh, okay, first let's talk about the game. It is important to say that chess is a face-to-face game. It is very close, so that usually you have to know the other player, and it requires a massive amount of knowledge. Part of this knowledge is theoretical or academic, for example, openings, but the other part of the knowledge regards the rivals. If you are a beginner, you don't care very much about the rival. However, if you're an amateur, you start taking care about who you are going to be playing with. And if you are a professional, you have to really care about who you are going to be playing. Just as a point in history, in 1997, the first computer beat the acting world champion at the time. Okay, so this is the board and the pieces. Most of us, I think that all of us know about it. And when we look at the first move, we have 8 different ways of moving pawns to the first line. And then we have another 8 ways to move pawns to the second line. So we have 16. And afterward, we have 4 different ways of moving the knights. So at the end, for the first move, we are going to have 20 possibilities for the white pieces and another 20 for the black pieces. If we look at the amount of moves, of positions, after the first move, we would have, uh, after the first move of whites, we would have 20, which you can arrive just by 20 different ways. After the first move of blacks, we have 400. After the second move of whites, we have 5,053, distinct moves, and you can arrive to them by 8902 total ways. So you can go on, and just to the third move, you can see millions of different positions. So let's represent the first move of the game in graphs. So what we're going to say is we're going to use a notation which is known as descriptive, which is quite old, but we just preferred. We had our reasons. So this move is the pawn king 4. So if the other one, the black ones, also move pawn king 4, you would say that you have a loop here. If you have another move, what you have is one node for the first move of the whites and an ending tied to the other node, which is in this case the move of the knight. So when you start getting different matches, for example, you can think in all of the matches of a player, or you can think in all of the matches of a tournament. You can start adding up these these ties so that you can have, for example, for these 3 matches, you would have this image or this little network. If you would think at the nodal degree, then in the case of the nodal degree or outgoing nodal degree, which is, for example, for this node would be 1, for this one would be 2 if we consider the loop, we have to take care into account the different replays that are going to to have the other player. So the out degree, it's the number of replays to the first move of the white pieces. The same happens with the black pieces. Just to say something about entropy, naturally, but about degree and diversity and disorder. Uh, Sorry, I don't know how to block that. Okay, so that okay, if I have to find my cell phone and I know that it is going to be in the bedroom, I have just one. My out degree is 1, and I have all of the information that I need. So I would say that the entropy would be 0. If instead I really don't know where I put seems that it has to do with, okay. Where did I leave my cell phone? In the bathroom, living, dining, bedroom, kitchen, yard. Then in this case, my out degree would be 6. And certainly I have much less information about where to look for my cell phone. So we can think in a measure of this kind amount of order of disorder in the second case, and we are going to define just a nodal degree entropy, just as usual. But look at one thing. When we look at the out entropy, or the one related with the out degree, we are looking really at the black pieces. Why? Because we're looking at the degree and the entropy related to this node, and the out degree will depend of the number of different moves of the black ones. So out would talk about black pieces, in would talk about white pieces. Okay, as we keep on taking these games, maybe we will have moves which are going to be, or combinations of moves which are going to be repeated, and then we can construct the matrix representations which contains the weights. It is the number of combinations of two moves, one for the whites and the other one for the black pieces. This would be, for example, the weighted matrix and the nodal strength for Karpov playing as white for all of his life. Here you have all the games of Karpov. So what is the nodal strength? Would be just adding these entrances of the matrix in the row. It would be what it will refer to what Karpov played as whites, and the replace would be in the nodal strength, but adding the columns. Okay, so we are going to define the strength of a node. This is lowercase s, so it is the strength, which is going to be related to adding just the weights of the combinations of the moves, which is. So I would call this, or we call this, what is the evident intention. It means it is what he really played. It is what Karpov played during all of his professional life as a chess player. So let's look now, for example, if I have to look for my cell phone, but I'm really not sure where I did put it, in the sense that there is a larger probability that I put it in the bedroom and lower one in the living room and so on. So then I have, let's say, the concept of weights in the case of graphs, and then I will define another entropy, which is related with the strength of the nodes. And in this case, this entropy would have as an upper limit the nodal degree entropy. So it is always going to be smaller than the previous one. This entropy will talk about the preferences of the players. In this case, if you talk about out, then it would be the preferences of the player playing with black pieces, and in would be for the white pieces. So let's see what happens with Olympiads. So this is, we are graphing here the entropy year by year. So we are having the tournament of each year in which the Olympiads were played, and we just measure the entropy. We have this one, which is the degree entropy out. It means it talks for the black pieces, and this is what we call the strength entropy. So you are going to see always that the stars are going to be at the upper level than the circles, just because they have to be larger. So what can we see here? First of all, so here we are playing blacks. Here we are playing what? Okay, this diagram tells about whites. How black pieces are playing, and in this case, how white pieces are playing. So what we notice is the maximum entropy obtained in this in the Olympiads in each year. It is closer in this case than if we look at the white ones. So what can we say? What we can say is that in some way, white pieces activate preferences, while the black pieces, they play by diversity. So if we look at the difference year by year of these entropies, what we're going to see is that at each time there are things happening. I won't tell you each one, but I will tell you that this is, for us, it is previous to Fisher, what we call the heroic time, and this has to do with the computer time. Maybe just to see that this function, this is the time in which the Soviet schools were formed by, like massively. So now we are going to do something different. We're going to get the cumulative graphs of all the games. So here we are going to have all of the games in the Olympiads from 1924 to the current year. So what can we see here? Okay, we have these entropies. We are comparing the first one, the degree entropy. Out, it means black. In, it means white. And what we see is that for the degree entropy, they are very close. Here we have 4 types. Here are all of the games. Then when we have green, whites, excuse me, this is in Spanish, white pieces 1, blacks, excuse me, blue, black pieces 1, and the red ones are for ties. When you look at the other entropy, the one that we associated to the strength, we see that you really can differentiate between them. And it means that here we are talking about diversity. Here we are talking about strategies. Okay, we are going to do the same thing in this case. We are having the same thing, but we are comparing these 2 entropies for blacks out, and we are comparing these 2 entropies for white. And when we interpret this as that really white pieces, they are applying their preferences. Okay, we see the difference, and we can follow a bit of the history of chess, at least from the Olympic chess games. Now let's see at the players. We already saw the tournament. Let's see the players, and we are going to see how these entropies evolve. And I would like to say about Anatoly Karpov, because we're going to have 2 players. He is convinced of the positional pressure. What does it mean? He really wants to get to a point where he can play at his own way. Let's see the other player that we're going to consider is Magnus Carlsen. And he says, I'm not that good at openings, but what I try to do is to place my pieces correctly on the board, so the advantage won't be so great that I lose immediately. Let's see the consequences of these 2 different ways of playing. Okay, this is the matrix, let's say the weight. Okay, this is the adjacency matrix. When Karpov plays whites, when he plays blacks, see, it is very different. Now, the weighted matrices, it contains all of the information of the network. He playing whites, playing blacks. Let's see what happens with entropies when we calculate entropies. Okay, we see that entropies are growing. It has to do with several things because he's exploring chess already as a professional. At a certain point, he will get to a comfortable place. Just look one thing. I won't explain in detail of this, but just look at this part of this graph. It is possible for entropy to increase and decrease even if we are accumulating all of the games in his lifetime. Okay, here is precisely his evolution. It is a young Karpov, fighting Karpov, and let's say an old Karpov. One, thank you. Then we have Carlsen, and you see which is the diversity. Okay, this is also Carlsen, and what we see in Carlsen is that he keeps on constructing himself. He keeps on evolving. So the ensembles, what we are going to say is to represent real systems with ensembles. What we do for doing that is to take the expected values for the ensemble to match the real properties of the system. In our case, we're going to have the networks, the ones that we saw. So what we do is have the real graph. We measure topological properties, which are going to be our constraints. And in this way, we construct the ensemble. I won't go through this part because we all have done it. But the point is that we have here the partition, the Hamiltonian, the partition function, and the partition function will going to be expressed in two new variables that we are going to call hidden variables, which depend of the Lagrange multipliers. So let's say what happens with that. These are the constraints, the real ones. This is how we calculate these quantities in the ensemble. And we define a new variable, taking in account that these two hidden variables, and this variable, we're going to call it hidden intentionality. So we are going to see what happens with players in the hidden intentionality. This is the way how it would look, the matrix of weights would look in the ensemble. And this is the way how intentionalities will change from left to right, white pieces, black pieces, black pieces. Carlsen, I would suggest that he has a much more diverse way of playing that Karpov. And I want to end to saying something about Olympiads. Now that we learned how to do this, to make this ensemble, we have to exploit it. And so we are going to see the intentionality for all of the Olympiads. And what we are going to see first is that the intentionality, the general intentionality in chess is stabilizing with time, growing and stabilizing. And we are going to take two other measures, which is the nodal degree symmetry, how symmetric are the ties of each nodes, the nodal, the asymmetry of the nodal out degree, nodal in degree asymmetry, and we are going to add the back. So we are asking the ensemble to tell us something. So what it's going to tell us is that it is growing with time, it is stabilizing, the asymmetry, the symmetry is growing. And when we look at the asymmetry, what we see is that there is an evolution of the asymmetry. Finally, when we look at the complete set, the whole system, what we look is that these symmetries keeps going on, keeps increasing. This is another measure which is related exactly with the strength. And what we are going to see in this measure is that there are changes with time in these two quantities, in the symmetry as well as in the asymmetry. So with this, I can conclude. Okay, the conclusion. Have different speeds. Good. Okay. The first move is the most important and most relevant of each game. It has all of the information of what the player knows about the other players. So it is, I can say half of the information, but it is a very important information. White, they would play with low diversity and high preference. Black would play with high diversity and low preference. What is happening with the history chess is that there is a positional asymmetry which is diminishing with time. And finally, there is a preference system which changed with time and is related to the fact that chess keeps being explored and it keeps evolving. So that's our conclusion. Thank you.
Thank you, Rafael. Nice talk. We have time for just one question. Oh,
I just wanted to know if there's any other motivation more than studying chess game. For example, if there's a possibility of generalizing this kind of study for other cases, for example, ecological dynamics or things like that, maybe, or I don't know, trying to predict other in business, I don't know, dynamics or something like that.
Okay, the original works were carried out by Diego Garlastelli and company, and they worked mainly on trade, the World Trade Network. And afterwards, it has been applied to several other systems. So what we really do is to take a method which already exists and to apply it to this system, which is chess. And I guess that it can be applied to many, many other systems. Thank you.
Okay, the next talk is by Lady Catherine Razo Hernandez. She's coming from the Universidad Nacional. Okay. Universidad Autónoma de México, sorry. His talk is about, her talk is about random walls on the network with preferential accumulated. This is the title. Okay.
Uh, Good afternoon. I am Caterina Erazo. I am a PhD student at the Universidad Nacional Autónoma de México. And today I'm going to present a part of my research work, which is called Random Walks on Networks with Preferential Cumulative Damage, Generation of Bias and Aging. So damage is an element that affects every system in nature, for instance, a system of roads, or also the human body. Although most of the systems have repair mechanisms, they are not perfect. So systems tend to accumulate damage with time, and this accumulation of damage affect their functions. Also, this accumulation of damage can be seen as the aging process. So in this context, it's important to understand how the functions of a system degrade as the system becomes damaged. And in our approach, we study random walkers on networks with damage. So networks are mathematically graphs. A graph is basically a set of nodes that are connected by means of edges. In this case, it's represented by means of this order pair ig, if the node I is connected with node g. N is the number of the network, and this quantity is the number of edges of the network. The topology of the network is represented by means of its adjacency matrix. Here we have the element aij of this adjacency matrix, which is 1 if the node I is connected with node j, and 0 on the contrary. Here I have an example of a network with 5 nodes. This is a directed network, so the arrows here represent the direction of the connections. And here we have its adjacency matrix. And for instance, we see here that the node 1 is connected with node 2. For that reason, the element A12 is 1. And on the other hand, the node 1 is not connected with node 4, so the element A14 is 0. Well, here I present the model of damage generation. The first thing that I want to say is damage is affecting the edges of the network, so it reduces the weights of the edges. Also, this damage is distributed in a randomly way and also in a preferential way, which means basically that if edge has a lot of damage, it's more likely to receive more damage in future. And as we see here, this capital letter is the time in which this damage process is happening. And also this letter helps us to count the number of faults that all the network has. Here I present two realizations of this process of generation of damage. The color in the links or in the edges represent a number of faults that each of these have. And this letter, Hij, it's related to the number of faults that the Hij has. And in this case, the fault appears in the Hij with this probability that it's in terms of the damage that the Hij already has. Well, in this situation, now we need to establish the matrix of weights for our network with damage that help us to understand the state of damage that this network has. And it's in terms of the adjacency matrix elements, AIJ. It's weighted with the amount of faults in the line IJ here. And here appears this parameter, which it can be seen as the intensity of damage that the network is receiving, or also it can be seen as the repair capacity of the network. For instance, in the case when alpha goes to 0, it means that the network is able to repair in a perfect way, so it does not accumulate damage. But if alpha goes to infinity, the damage is too severe, so we need to remove the line IJ. But we are interested in an intermediate case, so we are working with finite values of alpha. Now, for our random walker, we need to establish its transition matrix. Here we have this element, which is the transition probability for the random walker to go from node I to node J. And these elements, these transition probabilities, are in terms of the weights of the network with damage. In this case, the damage is affecting the symmetry of this matrix. So now this matrix has complex eigenvalues that are complex numbers. And here I have two realizations of this process in which we see the evolution of these eigenvalues, particularly for a Barabasi-Albert network, which is a random network, in this case with 50 nodes. And here we see the imaginary and the real part of these eigenvalues as the damage increase in the network. Here in the real axis, we see these circles, which corresponds to the eigenvalues of this transition matrix for the case of the network without damage. Well, this asymmetry in the process of the random walk can be measured with, here I show only two measures that we have implemented. Here I have a local measure, which basically compares the elements Ij and Ji of the transition matrix of our random walker. And here I have a global measure, which compares the mean first passage times of the random walker to go from node I to node J and vice versa. Here, the mean first passage times basically tell us the average number of steps that the random walker needs to go from node I to node J for the first time. And it can be calculated in terms of the right and left eigenvectors of the transition matrix. And here we have the eigenvalues of this matrix too. And here we find the stationary probability for this process, which basically tells us the probability to find the random walker in the node J after a long time. And here I present the evolution of these asymmetry measures. Principally here, this blue line and this black line are the measures that I already talked. And we see here that these measures decrease with this time or the number of damage in the network. And these results basically tell us that as the network becomes damaged, the process of the random walker, the asymmetry of the process of the random walker increases. Well, now we've established a measure that help us uh, to to understand how is the transport capacity of these networks with damage. In this case, we use this functionality, which is basically a rate between the global mean time for the random walker in the network without damage over the global mean time of the random walker in the network with damage. This global mean time basically tells us the number of steps that the random walker needs to reach any node of the network, and it is a weighted average of its mean first passage time, as we see here. And here I present the evolution of this quantity. This dotted line is the ensemble average of these 1,000 realizations that we have here. And the results here show us that the damage produces a reduction in the transport capacity of the network. Well, then this measure of functionality can be used to establish a classification of different structures according to their robustness under this model of damage. For doing that, we have here a normalized functionality. Here it is the average ensemble of this functionality for a particular value of damage. And here we have the edge density of the network, which is calculated in terms of the number of edges of the network over the number of edges of a complete network with the same number of nodes. And here we have the results for these 6 structures. The weakest structures here is this barbell graph. It corresponds to it's formed by 2 complete graphs joined by mean of this chain. And if we think in this part, if we damage this part, for instance, it's probably that the random walk gets trapped in one of these complete graphs. So it's affecting in a several way the transport capacity of this structure. But then we start to find these different structures here. Here we have a ring graph, and these are random networks. And finally, we find this wheel. And as we see here, all these structures are have a more complex topology. And also we have that there are more paths that connect each pair of nodes, also have more cycles. And all these mechanisms are behind their robustness. Well, we use this measure of normalized functionality in another way, in another work, when we use this to classify several metro systems that we have here. And but well, this model of damage generation it's general, so we can apply this to study different dynamical processes. Here I have an example where we was working in the effects of damage in the synchronization process of networks of Kuramoto oscillators. Well, yeah, that's what all that I want to tell us. So to sum up, we study a preferential cumulative damage process. As we see, this damage increases the symmetry of the random walk process, and also we see that it reduces the transport capacity of networks, and we can apply this to other dynamical processes, such as in this case, synchronization. Thank you.
Thank you. Questions?
in these directed networks, you do have two adjacency matrix, the in adjacency matrix and the out adjacency matrix. No, depending on which is it. Does it matter? Doesn't matter which one you take.
Sorry?
For these directed networks, there exist two adjacency matrices, namely the incoming adjacency and the outgoing adjacency. Which one do you choose, and does it matter which one to choose?
Well, we are using or we are considering the directions when we are start to damage each of the edges. So, for instance, in this case, for instance, this edge and this edge are different. So when we are working with the matrix of weights, we are considering both directions there.
Thank you. I'd like to know if you have analyzed perhaps the effects of modularity in networks. For example, if you have subsets in your network. For example, that's the example like in higher organisms and living systems. So I would like to know if you have like analyzed some kind of the effects of modularity in damaging the edges of these kind of networks.
Do you mean that use damage just
yeah, I mean,
parts
for example, if you have a complex network, but that's divided in subsets and subgraphs, or yes, communities or perhaps organs or something. I mean, it depends a lot of the system. But since you made the example of living systems at the beginning of your presentation, I'd like to know if perhaps you have analyzed the effect of this modularization in damaging certain edges in the network. For example, if that's worse or better from the functionality of the whole network having this modularity.
Well, this is a working process. Here, the damage is affecting all the network, but the idea is to extend all these ideas to analyze, the effect just in certain localized parts of the networks, as you say, maybe communities, and see what happens there. But it's just a work in progress.
Okay, thank you.
I would like to know if you know, or like, why is the damage done on the edges and no on the nodes? Like, why is there a reason for that to be defined like that, or you just for the type of problems you want to solve with this, you think it's more convenient to do the damage on the edges but not in the nodes? And if you have considered maybe a model where the damage is done on the nodes of the graph.
Okay. Well, this model applied or it's affecting the edges because we're considering the relationships between the nodes. For instance, in the case of metro systems, we are considering, well, here these nodes represent the terminal and the transfer stations. So we are considering that the damage is in all the information that get or are in between these nodes that correspond to the other stations. So all this damage is produced by this part specifically. So we are considering this. There's the damage in the relations of the parts of the networks, of the parts of the system, basically.
Question? You consider the resilience in the resilience?
Well, we are here. We are analyzing more that the resilience, the robustness of the structures, not the capacity to recover from damage, but it can be a good work for the future.
Actually. Okay. The next coffee break. And is in the physics building. Yes, in the physics building, en el edificio de física, en el 405, por favor.